In this video, we're going to discuss Pythagorean identities and the period of trigonometric functions. So we're going to start with Pythagorean identities. Recall that the Pythagorean theorem is a squared plus b squared is equal to c squared, where a and b are the legs of a right triangle, and c is the hypotenuse of that right triangle. If we draw down a unit circle here, we might recall that for some theta, for a given theta, we can look at the triangle for that theta. Well, if we look at this triangle, this is a right triangle. We have legs of length x and length y in the appropriate spot here, and then the hypotenuse has length 1. So, what can we do? Well, we might also recall that x is cosine of theta, and y is sine of theta. So, this formula, which using the Pythagorean identity would be x squared plus y squared is equal to 1 squared, which is x squared plus y squared is 1. Well, this becomes cosine squared of theta plus sine squared of theta is equal to 1 when we replace x with cosine theta and y with sine theta. And this is what is known as a Pythagorean identity. We actually have two related identities to this, which I will say now. So I'm going to rewrite that same identity, and then we're going to do something to it and get a new identity. Well, let's divide everything by cosine squared. So we divide both sides by cosine squared, and we get cosine squared over cosine squared is 1 plus sine squared over cosine squared. Well, sine over cosine is tangent, so this is tangent squared. And 1 over cosine is secant, so this is secant squared. And we get a second Pythagorean identity. And we're going to do the same thing again, but we're going to divide by sine squared. Cosine squared over sine squared is cotangent squared. Sine squared over sine squared is 1 equals, whoops. And 1 over sine squared is cosecant squared. And so we get a third identity here. Great. Now, what can we do with that information? Well, how about we try to do an example? So this will be example 1. Right? These identities were true for any angle theta. So we'll start with a really simple example, and that is, what if we were asked to simplify cosine squared of pi over 8 plus sine squared of pi over 8? What if we're asked to simplify that? Well, cosine of pi over 8 might be difficult to find, so it might seem like cosine squared of that it would be difficult to find, and thus, similarly, sine of pi over 8 would be difficult. But, as we said before, cosine squared of theta plus sine squared of theta is equal to 1 for any angle theta, so if we have cosine squared of pi over 8 and plus sine squared of pi over 8, those are the same angle, this is in fact 1. And there's no work to be done. Okay? So, let's move on to example 2. if 0 is less than t is less than pi over 2, and sine of t is equal to 7/8, what is cosine of t equal to? Well, to solve that, we use this Pythagorean identity again. Sine of t is 7/8. Well, how do we, and we need to find cosine of t. Do we have a formula that relates these two? We do. It is cosine squared of t plus sine squared of t is equal to 1. Well, this is cosine squared of t plus sine of t is 7/8, so this is really 7/8 squared is equal to 1, which in fact is the equation cosine squared of t plus 7/8 squared is 49/64, and this is equal to 1. So cosine squared of t plus 49/64 is equal to 1. If we subtract 49/64 on both sides, this 1 would be 64 over 64, so 1 minus 49/64 is 15/64. So cosine squared of t is equal to 15/64. If we take the square root of both sides, recall that the square root of cosine squared of t, the square root of a square is just the absolute value of that thing. So this is the absolute value of cosine of t. So if we take the square root of both sides, we get the absolute value of cosine of t is equal to square root of 15/8. So then the question is cosine of t positive root 15/8, or is cosine of t negative root 15/8? And we got to look back up at this statement here for that. If 0 is less than t is less than pi over 2, well then if we look back at our unit circle, t is between 0 and pi over 2. That means it's in the first quadrant. If we look at the first quadrant, what is our cosine value? Our cosine represents x, so cosine is positive. So in fact, the answer is the positive version of the solution that we got. And that ends our 2 examples for Pythagorean identities. Next, we're going to talk about the period of a function, specifically the period of trig functions. You should go read the definition of a period if you haven't already. You should do that now. But essentially, what is the period of a function? Well, a period of a function is the smallest value that when we add it to the input, we get the same output every time. Let's think about what that might be in terms of circles. So suppose we have some theta here. If we have some random theta here and we add 2 pi to that, we get back to the same point. So, and no matter where we're at on the circle, if we add 2 pi, we always get back to the same point. So certainly, the period of cosine and sine may be 2 pi. Now specifically, the period is the smallest value where that happens all the time. And in fact, 2 pi will be the smallest value where that happens all the time. So what we can notice is that cosine of theta is equal to cosine of theta plus 2 pi, no matter what the original theta was. Similarly, sine of theta is equal to sine of theta plus 2 pi, no matter what that original theta was. Now, interestingly enough, you might also notice that what if we started at theta is 0 and we found sine of that? Well, sine of 0 is 0, right? The y value here is 0. what is sine of pi? What if we just added pi? Let's add pi. Then we move over to here. What is sine of pi? Well, that would also be 0. So you notice that if we start at 0 or pi, or any multiple of pi, and we add pi to it, we always get back to one of these two spots, here and here. And sine of both of those values is 0. So you might think, oh, maybe the period of sine is pi, because every time I add pi, I get back to the same output, the same value. But that's not true everywhere else. So if I pick another spot up here, and I add pi to it, then I'm going to go halfway around the circle, and I'm going to be down here. Sine is not going to have the same value here. It's positive up here, and it's negative down here. So they're certainly different. So the period of sine can't be pi. Because, again, it doesn't work for every angle theta. But if you add 2 pi, that will get back to the same sine value everywhere, no matter what that theta is. So, and similarly for cosine. So what does this mean? The period of sine and cosine is 2 pi, and the period of secant and cosecant is also 2 pi. It's a little different for tangent and cotangent, though. The period for tangent and cotangent is just pi. This repeats every pi instead of 2 pi. Let's use those, or that piece of information, for an example. So this will be example 3 and the final one for this video. We're going to ask ourselves to find the exact value of, and A is going to be cosecant of 9 pi over 4. Okay. Well, how do we do this? We notice that cosecant has a period of 2 pi. So, if we add or we subtract 2 pi to this value in here, we get the output will be the same. So cosecant of 9 pi over 4 is the same as cosecant of 9 pi over 4 minus 2 pi, which I'm going to write out as 8 pi over 4. This is equal to cosecant of just pi over 4. And now we're back in between 0 and 2 pi. So this will be easier to find. Notice this is the same as 1 over cosine of pi over 4 by our definition of cosine. Well, what is cosine of pi over 4? Cosine of pi over 4 is root 2 over 2. So this right here is 1 over root 2 over 2, which is the same as 2 over root 2. You might also see this version, where if we multiply by root 2 over root 2 here, we get 2 root 2 over 2, which is root 2. So you may also see that as an answer, but 2 over root 2 is fine for me. But this is the exact value of cosecant of 9 pi over 4. All right, let's do another one. What about tangent of negative 9 pi over 4? Well, this is the same as, well, again, we can add pi. So let's add pi, which is 4 pi over 4. That is tangent of negative 5 pi over 4. Okay, we can add pi over 4 again. So negative 5 pi over 4 plus 4 pi over 4. So we get added pi again. This is tangent of negative pi over 4. All right, what is tangent of negative pi over 4? Let's draw our unit circle. Note that positive pi over 4 moves to this angle. Negative pi over 4 moves to here. At this point, we see that this is tangent of negative pi over 4 is the same as sine of negative pi over 4 all over cosine of negative pi over 4. Well, sine of, oops, sorry, I was off the page. I was off the video. So we have our negative pi over 4 angle here. And sine of tangent of negative pi over 4 is the same as sine of negative pi over 4 divided by cosine of negative pi over 4. Well, sine of negative pi over 4, if you remember from the previous video, this is negative sine of positive pi over 4. Cosine of negative theta is the same as positive cosine of positive that theta. So this is just cosine of positive pi over 4. Which is negative tangent of pi over 4. Tangent of pi over 4 is 1, so this is negative 1. We could have gotten this a lot simpler if we had just remembered that tangent of negative pi over 4 is negative tangent of positive pi over 4, and we didn't have to do these previous steps. But I think this was nice to write out so that we see what's going on. Get a little bit more practice. Okay, well, I'm going to do one more example, part C of this. So we're going to call this part C. And that is find the exact value of sine of pi over 4 minus 2,000 pi. Oh, that seems crazy. Except that when we add or subtract any multiple of 2 pi, we get back to the same output value here. So if I take sine of pi over 4 minus 2,000 pi, that's the same as if we added 2,000 pi, which is 1,000 times 2 pi, back, we'll get the same value. So this is just the same as sine of pi over 4, which is root 2 over 2. And we can calculate that quickly. All right, and that is it for this video.